For centuries, the standard scientific model was built on reductionism, the idea that any whole can be understood completely if you understand its parts. Isaac Newton and Pierre-Simon Laplace envisioned a world that functioned like a giant, predictable clock. The logic was simple. If you know the starting positions and the forces acting on every particle, you can calculate the future of the entire system. In this view, the universe is a machine that was wound up at the beginning of time and has been following a set path ever since. But living systems ignore this mechanical blueprint. A swarm of 500,000 army ants can build complex bridges and nighttime shelters, yet there is no commander and no master plan. Each ant is nearly blind and minimally intelligent, yet the collective creates a sophisticated, coordinated mass. This gap between the part and the whole is why reductionism fails to explain things like human consciousness. Examining a simple, microscopic neuron tells us very little about how trillions of them work together to produce thought. You cannot find intelligence by looking at a solitary cell. To understand reality, science had to look past the clockwork model. Researchers had to reconcile 3 specific discoveries from the 20th century that set physical and logical limits on what we can ever truly know about the future. The first limit is known as chaos theory. It showed that even when the rules of a system are simple and known, the results can be impossible to predict. In a linear system, the whole is the sum of its parts, like adding flour and sugar. But nature is often nonlinear, where the parts interact. A population of rabbits doesn't just grow, it eventually hits limits of overcrowding and resource depletion that change how the system behaves. This is the logistic map, an equation used to model that growth. As the birth rate increases, the population size stops being a single, stable number. It begins splitting into a period of 2 alternating sizes, then 4, then 8. This is the period doubling route to chaos. Once a system becomes chaotic, it develops a sensitive dependence on initial conditions. If you start the same equation twice, but change the starting value by just 1/1000th of a decimal, the outcomes will eventually diverge until they have no correlation at all. Even in this unpredictability, there is order. The physicist Mitchell Feigenbaum found that the rate at which these systems split is always the same. This number, Feigenbaum's constant, appears in the behavior of fluid flow, lasers, and even human heartbeats. Because we can never measure the world with infinite precision, Laplace's dream of perfect prediction is a physical impossibility. Nature operates within a chaos that is both unpredictable and mathematically structured. The second limit concerns the boundaries of logic. In 1900, David Hilbert proposed that every mathematical statement could be proven or disproven by a definite procedure. He believed there were no unsolvable problems. Alan Turing tested this by defining exactly what a definite procedure actually was. He created a blueprint for a programmable computer. His Turing machine used a read-write head to process symbols on an infinite tape based on a set of rules. It was a model of pure logic, showing how a machine could take an input and compute an answer. Turing then proved the existence of the halting problem. He showed it is logically impossible to write a program that can look at any other program and determine if it will eventually finish its task or get stuck in an infinite loop. Some questions are simply uncomputable. Uncomputability means there are strict boundaries on what logic can solve. Just as chaos limits our physical predictions, Turing showed that some systems are too complex to ever be pre-calculated. The third limit is the discovery that information is a physical commodity. It is bound by the same laws of thermodynamics that govern energy and heat. This is Maxwell's demon, a thought experiment where a tiny entity creates order out of disorder by knowing the speed of gas molecules. By sorting the fast from the slow, the demon seemingly decreases entropy without doing any work, which violates the laws of physics. Leo Szilard resolved this by showing that the demon's knowledge has a price. To identify a molecule as fast or slow, the demon must acquire 1 bit of information, and that act of measurement requires a physical transaction. Landauer's principle later proved that the real cost is memory. To keep sorting, the demon must eventually erase its data, and the act of erasing a memory physically generates heat. Creating order in one place always increases entropy somewhere else. Information processing is a physical act. Building an intelligent, organized system requires energy, meaning every thought and calculation carries a strict thermodynamic cost. At first, these limits felt like a retreat for science. Chaos, uncomputability, and the cost of information seemed to put the most interesting parts of the universe forever out of reach. But we now see these constraints as the rules of the game. On a trading floor, thousands of independent actors process local signals and personal information. They don't need a central controller to create a global market. The order emerges from the decentralized interaction itself. Living systems thrive because they operate within these boundaries. Instead of pre-calculating a chaotic environment, biological networks use local information to adapt in real time. Complexity is the result of systems organizing and solving problems without needing to be predictable. We inhabit a self-organizing network that builds itself from the bottom up. By studying the limits of what we can predict, we begin to see the rules of how complexity actually works.